Continuing with 1.5, still working with slope, still working with some linear equations towards the end of this part, but not so much with parallel and perpendicular are still around. But the new idea that's being introduced that you probably have not seen in Algebra 1 or Algebra 2 is the idea of an average rate of change for a function when you're moving between two x coordinates that are handed to you. So from the textbook, or if you Google this, there's no real reason to because I provided it for you. The average rate of change we still denote as the change in y over the change in x. So similar to slope, where we're now going to be evaluating those two x terms that are given to us. They denote x1 as 2, x2 as 6 for the function f of x, where x squared minus x plus 4 is that function. Really what you're doing here is just plugging and chugging in values and then just taking the difference between the y coordinates and the x coordinates. So if you want to plug in those numbers and evaluate it, go for it. How I personally approached this to save time and save work was on the calculator. So where I hit y equals, I put in the actual function x squared minus x plus 4. Again, just typing that in, that's nothing too crazy. If we then hit second and then graph, this then hands us over to the table where if we're looking at this first set of values here, when x is 2, the outcome is 6. So I have that written down. I also found when x is 6, the outcome's 34. So I have those terms that I need. I know the x terms that are given. I know the outcomes that are given accordingly. So if we plug in everything that we have, f of x2, that outcome was 34. So if we have 34 and then we deduct the outcome from when x was 2, that outcome is 6. Taking this further for x2 and x1, so 6 minus 2. 34 minus 6 is going to get us 28. Dividing this by the difference of 6 and 2, which is going to be 4. 28 over 4 is going to get us 7. So 7 is considered our rate of change. Eventually, when you're in calculus, you'll be finding what this really means. And if you need a visual representation, we can graph this out. So we see that the quadratic is there. We then see this additional line that's going up and to the right. So we'll try to trace this. So we see that this line is moving up and to the right. Let's see if we can zoom in a little bit. So we see the linear equation, and we also see the quadratic. So what this line is if you recall from calculus, or no, from geometry, the line that's going up and to the right, kind of working between where x is 2 and where x is 6, is considered the secant line. So secant line's coming back into play. So eventually, when you take calculus, you'll see that this secant line is kind of similar to tangent line from geometry. And this is from geometry. So if you recall that from geometry, that's cool. But I'm just really taking this idea further where this 7 ends up as the slope for the secant line. And again, this portion here is extra. It's just so that down the road, if you see this, you might say, oh, that's what I was given there. So this problem's done. Our final answer, that final rate of change between where x is 2 and x is 6 is 7. We're done on that. For the second problem, this has a little bit more going on with graphing. So they give this graph of f, and it's passing through the point 2, -5. This is running perpendicular. So we know that the slope of those two lines is going to equal -1 when multiplied. There's an x-intercept of 4. Y-intercept of -1, and we're being asked to find the slope-intercept form of this equation. So We have some options here. Let's take some time to really focus on what's going on. Let's even reread this. So the graph of f passes through 2, -5. So if we denote through a table, let's say that we have one point that it's going to have to hit 2, -5. We can even graph this out. So 2, -5, got that. And we know that this is going to run perpendicular to the line that has an x-intercept at 4 and a y-intercept at -1. So this is talking about another line. This line is different than f of x. So this is a different second line. Please do not confuse this with f of x, because it would look awfully goofy if you try to have 2, -5 on the same line that has an x-intercept of 4 and -1. So we'll try to denote the second line using red. I know that the x-intercept's 4. And I know that the y-intercept's -1. They don't necessarily give you the type of line it is, of g of x or h of x, whatever, but let's just call it the other one. We know that we have these 2 points on there. So we'll start first with the x-intercept. When x is 4, the outcome 0. When y is -1, then outcome is 0. Just a little bit of information to seal this deal. We know that we can get a hold of this slope if we use rise over run. So if we move over once, twice, 3 times, 4 times, our run for the second line is 4. Our rise for that second line is 1. So from here, we can denote the slope for that second line as positive 1/4. We could also extend this line if we want, just to show that we know this continues in both directions. The more examples you have for a problem, the better. Going back to the main objective, we're trying to find the graph in slope-intercept form, so the function f of x. And we still want to find and make sure that this runs perpendicular. Well, we know that if the one slope for the other line is 1/4, we can definitely get a hold of that second slope. So we'll denote this as m2. We know that this needs to be the negative reciprocal of this one. So if the slope of the other line is 1/4, this is going to have to be -4. Flipping around, 1/4 would be 4. Switching the signs would make it negative. So we know that our slope is -4. We can continue this idea and start to piece together what this will look like. If the slope's -4, it's going to go over 1, eventually going down 4, but in this case, we'll backtrack. Just sketching this out so we have a visual. So notice I'm color coordinating accordingly. For f of x, I'm using black. For the other line, I'm using red. So we know that, just to fill in some other points on this, we would have 1, -1. We would also have 0, 3. And I think that'll be good. So we want this equation in slope-intercept form for f. We're actually lucky, since we backtracked, we found that the y-intercept is going to be 3. So that's our b term. If we start to piece this together, f of x is definitely going to be needing that slope of -4. And we also have that y-intercept of positive 3. So getting us an equation of negative 4x plus 3. I like these types of problems because you really have to think out what you're trying to get. Notice that we didn't have an equation handed to us. We just plotted some points and kind of made some moves from there. We used slope again, which was cool. We also tied in the idea of using perpendicular lines, eventually getting back to the main objective, which was making the equation in slope-intercept form for f, which is what we did with negative 4x plus 3. So a lot of stuff going on in this example, but take your time, think of what you know, think of what you might need to reread, and be patient because this does get tricky, but you got it.